Welcome back, everybody. Today, we're taking a deep dive into the world of computer vision,
Okay.
specifically a PhD dissertation that really caught my eye.
Mm-hmm.
It focuses on making convolutional neural networks,
Yeah.
you know, those CNNs,
Right.
more robust and fair,
Okay.
interpretable and explainable.
Sounds interesting.
And what's really cool about this dissertation is that it's very application-focused.
Oh, cool.
It's not just theory.
Right,
You
right.
know, it dives into real-world use cases.
I like that.
And I know you're particularly interested in this.
Yeah.
It looks at vulnerabilities in classical computed tomography.
Okay.
Now, before we get into the specifics,
Sure.
this dissertation covers a lot of ground.
Okay.
I mean, it examines a bunch of different applications of CNNs.
Interesting.
Just to give you a taste, we've got mitigating motion-induced artifacts in cone beam computed tomography,
Wow.
homogenizing CT scans for improved cross-dataset analysis,
Mm-hmm.
and even stuff like pre-training techniques for motion recognition. It's really wide-ranging.
Yeah. Impressive.
But what really stood out to me, and I think this is where we should start, is the author's use of radial basis function networks.
RBFs.
Yeah, exactly.
Hmm.
To make these CNNs more explainable.
Right.
It's a pretty novel approach.
It is. RBFs have been around for a while, in like classical machine learning,
Yeah.
but using them with deep learning models, not so much.
Yeah.
There have been these,
Technical difficulties.
technical difficulties.
Okay, so that's what the dissertation calls it, technical difficulties.
Uh-huh.
Can you unpack that a little bit
Sure.
for our listeners who might be super familiar with CNNs,
Mm-hmm.
but maybe not so much with RBFs?
Right. Well, the main problem has been getting traditional RBFs to play nicely with backpropagation, which is like the bread and butter of training deep learning models.
Yeah, you need that.
You do. And the thing is, traditional RBFs, they usually use these non-linear activation functions. And those can cause all sorts of problems during training, like vanishing gradients or exploding gradients.
Right, makes sense.
So it gets messy.
So how did this author get around that?
Well, they did something pretty clever. They introduced a quadratic activation function for the RBFs.
Good.
And this function, it's linear with respect to the squared distance.
So compatible with backpropagation.
Exactly. It solves that whole issue.
So they basically redesigned the RBF architecture
Yeah.
to work within a deep learning framework.
It's not just the activation function, though.
No, there's more.
They also came up with this really cool training approach that combines supervised and unsupervised learning,
Interesting.
which makes the RBFs even more effective in this deep learning context.
It was like a total overhaul.
Pretty much, yeah.
So they've got these RBFs working.
Mhm.
They're training them in this new way.
Right.
And now they're using them to build this visual similarity distance metric.
Yeah. Have you seen figure 3.1 in the dissertation?
I have. It's pretty cool.
It basically shows how the model can look at an image
Right.
compared to a bunch of other images and
Yeah.
figure out which ones are similar and which ones are different.
Like a visual search engine, but powered by RBFs.
Exactly. And what's really neat is that this whole similarity thing,
Yeah.
it's actually built right into the classification process itself.
Woo, that's really clever.
It is.
So the similarity distance metric makes
Mhm.
me think of deep metric learning.
Good connection.
How does this specific metric relate to, like, other distance metrics?
Yeah, so in deep metric learning, you're basically teaching models to figure out how far apart data points are.
Right.
And in this case, the data points are images.
Mhm.
So you've got your classic metrics like Euclidean distance
Yeah.
and cosine similarity.
Okay.
But with this RBF approach,
Right.
it's all part of the classification.
So it's like baked in.
Exactly.
That's amazing.
Yeah, it's pretty cool.
So we've talked about explainability with RBFs.
Mm.
Now let's move on to another big challenge in AI robustness.
Okay.
Adversarial attacks.
Oh, yeah, those are tricky.
They are, where you make these tiny little changes to an image
Right.
that are almost invisible to a human.
But they completely fooled the CNN.
Exactly. And that's a huge problem for real-world applications.
Absolutely. How do you trust a system that can be tricked so easily?
Right. So how does this author deal with that?
Well, they use this really cool concept called feature response maps,
Okay.
which basically show you what parts of an image the CNN is focusing on.
So like a heat map?
Kind of, yeah. It highlights the areas that are important for the CNN's decision.
And how do you create these feature response maps?
Through something called guided backpropagation.
Which is...
It's basically like running the CNN in reverse.
Oh, interesting.
To see which parts of the input image led to the final output.
Okay, so you can trace the decision-making process.
Yep. And that's what makes this approach so explainable.
I see.
You can actually see why the CNN made the decision it did.
Unlike some of those black box methods.
Right.
So let's jump to table 4.1 in the dissertation.
Okay.
It has these really striking examples of how adversarial attacks mess with these feature response maps.
Yeah, it's pretty eye-opening. You see these pairs of images,
Right.
the original and then the one that's been tweaked.
Yeah, the perturbed one.
Right, and you can barely tell the difference.
Yeah, it's like a couple of pixels.
But then you look at the feature response maps, and they're completely different.
Yeah, the CNN is focusing on totally different things.
Exactly. It's crazy how these tiny changes can have such a huge impact.
So the author can visualize these vulnerabilities, but they don't stop there.
No.
They actually come up with a way to automatically detect these attacks.
Right, using the feature response maps.
Okay, how does that work?
Well, they calculate something called average local spatial entropy from the maps.
Okay.
And if that entropy suddenly spikes...
Red flag.
Exactly. Red flag, something's fishy.
It's like the CNN is freaking out.
Yeah, kind of, because it's not sure what to focus on anymore.
That's fascinating.
It is. And again, what's cool is that it's explainable.
Right, we understand why the alarm is going off.
Exactly. Not just some mysterious black box saying, "Danger, Will Robinson."
I love that analogy. So this is a great example of how understanding how CNNs work can lead to practical solutions for making them more robust.
Absolutely. We're not just diagnosing the problem.
Right.
We're actually fixing it.
Now let's shift gears a bit
Okay.
and talk about another area where the author made some really cool contributions, mitigating motion artifacts in CBCT scans.
Ah, that's a big one, especially in radiation therapy.
You're right. I know this is a topic you're particularly interested in.
I am.
So these motion artifacts, they happen when the patient moves during the scan.
Right, which can be a problem.
It's a big problem. They distort the image, and that can mess up treatment planning.
Exactly. You need those images to be accurate.
Absolutely.
Yeah.
And the thing is, there's no easy analytical solution to this.
Yep.
All those classical reconstruction techniques like FDK, filtered back projection, or ICP-CT, iterative algebraic reconstruction technique, they all assume the object is staying still.
Yeah, which is not realistic.
Not in the real world, so they don't handle motion very well.
Not at all. That's where deep learning comes in.
Right. This is where the author's approach gets really interesting.
Okay, I'm intrigued.
They use 4D CT scans.
4D?
Yeah, which capture multiple phases of motion.
Oh, clever.
To create training data for their models.
So they're basically simulating motion artifacts.
Exactly. They take these 4D scans, which are pretty much free of motion artifacts.
Right, because they're capturing the motion.
Exactly, and they introduce simulated movements based on, real patient breathing patterns.
So they're making the scans look like they have motion artifacts.
Exactly, and then they use those motion-corrupted scans.
Along with the original 4D scans as the ground truth.
To train their deep learning model.
Oh, wow, that's brilliant.
And these models are based on what they call refined UNet architectures.
UNet, okay.
Can you explain why they chose UNet for this and how they actually trained these models?
Sure. UNet architectures are really good at image-to-image translation tasks.
Like this?
Yeah, where you're basically mapping an input image to an output image.
Right.
And they're great at capturing both global context and local details.
Which is important for
getting rid of those pesky motion artifacts.
Okay, so the architecture makes sense and the training.
Well, they created this whole deep learning pipeline.
Oh, cool. Tell me about it.
It's got 3 main parts, a projection enhancement network, or PENet for short.
Okay.
And there's a volume enhancement network, that's the VENet.
Got it.
And then they tie it all together with this dual domain optimization approach.
Dual domain, huh?
Yeah, if you look at figure 5.2 in the dissertation, it shows the whole pipeline visually.
So break it down for me. What does each part do?
All right, so the PENet, it works on the 2D X-ray projections.
Before the 3D reconstruction?
Exactly. It's like a pre-processing step.
Okay.
It tries to clean up those projections by correcting for motion artifacts, but in the projection domain.
In the projections themselves?
Yep. Then those enhanced projections,
they
get fed into a classical reconstruction algorithm.
Like FDK or ICP-CT?
Right, to create a 3D volume.
Okay.
And then that volume goes into the VENet.
Ah, so it's like a 2-step process.
Exactly. The VENet takes that initial reconstruction and it refines it further to reduce any remaining artifacts.
So you're tackling artifacts in the projections.
Uh-huh.
And then again in the 3D volume.
Yep. Dual domain optimization.
And that's where the real magic happens.
The cool part is that they train the PENet and the VENet together.
At the same time.
Yep, using supervised learning.
So they're learning how to work together.
Exactly. They complement each other.
That's amazing.
And the results are impressive.
So it works.
It does. They saw significant improvements in image quality.
Like what kind of improvements are we talking?
Well, they got up to a 6.3 dB increase in peak signal-to-noise ratio.
That's PSNR.
Yep. And a 0.19 improvement in structural similarity index.
SM.
Right? For both FDK and ICBCT reconstructions.
So that means clearer images.
Definitely more reliable, too.
Which is crucial for
accurate diagnosis and treatment planning.
In radiation therapy.
You got it.
This is really impressive stuff.
It is. This author is doing some amazing work.
And it's not just limited to motion artifacts.
No.
Chapter 6 of the dissertation covers a bunch of other applications.
Really? Like
emotion recognition.
Wow.
Auto ML.
Okay.
Even fairness in facial recognition systems.
That's a hot topic.
It is. It shows how versatile this author is.
Yeah, and how widely applicable their research is.
We probably won't have time to dive deep into all of that today.
Right.
But can you give us a quick overview of the work on homogenizing CT scans?
Sure. So this is all about dealing with variability across different CT data sets.
Which is a problem for...
It's a big problem for deep learning models. Because if you train a model on one data set and then try to use it on another one, it might not work very well.
Why is that?
Because the data sets might be different, you know?
In what way?
Well, the scanners might be different. Or the acquisition protocol.
Or the patient populations.
Exactly. So the images might look different, even though they're supposed to be showing the same thing.
So how did the author address that?
They used convolutional autoencoders.
Interesting.
To learn a shared latent representation across the different data sets.
So they're basically making the scans more similar.
Exactly. Homogenizing them so the models can generalize better.
That's pretty clever.
It is.
And speaking of clever, let's talk about emotion recognition.
Okay.
The author uses echo state networks for this.
ESNs? What ESNs?
Yeah, it's not the most common approach.
It's not, but they're computationally efficient.
Which is important for
real-time application.
Like emotion recognition.
Exactly. You need to be able to process the data quickly.
So the author is prioritizing speed.
Yeah, without sacrificing performance.
So how do ESNs actually work for emotion recognition?
Well, they're really good at processing sequential data. Like audio and video streams.
Okay.
So they can pick up on those emotional cues.
Like the tone of voice.
Yeah, or facial expressions.
It's like having an AI that can read between the lines.
Kind of. It can understand the nuances of human interaction.
That's pretty cool.
It is, and it gets even cooler.
Well, there's more.
The author also explored multimodal information fusion.
Multimodal.
Yeah. So instead of just looking at one type of data.
Like just audio.
Right. They combine data from multiple sources.
So like audio and video.
Yep. And even physiological sensors.
To get a more complete picture.
Exactly. Because emotions are expressed in so many different ways.
Right. It's not just what you say, it's how you say it and your body language and everything.
Exactly. So by combining all this information,
you get a more accurate assessment.
Precisely.
This is getting into some really advanced stuff.
It is.
Okay, now let's touch on another really important topic.
Okay.
Fairness.
Ah, yes, a crucial one.
Especially when we're talking about facial recognition systems.
Right. There have been a lot of concerns about bias.
There have, and this author dives right into that.
Good.
They talk about the difference between racial awareness and bias.
Okay, can you explain that?
So racial awareness means the system can recognize different races.
Okay.
But bias means it treats people differently based on their race.
Ah, that's an important distinction.
It is, and the author's point is that just blinding the system to race doesn't necessarily solve the problem.
It doesn't. You have to address the underlying causes of bias.
Which are?
Well, they can be in the data itself. Or in the algorithms.
So it's a much deeper issue.
It is. You have to be really careful about how you design and train these systems.
And evaluate them.
Right?
Okay, so fairness is a big one.
Huge.
Now let's talk about automated data analysis.
Auto ML.
Yeah, auto ML and auto DL.
Okay, so this is all about automating the process of building and deploying machine learning and deep learning models.
It's like AI building other AIs.
Exactly.
That's kind of mind-blowing.
It is, and it's becoming more and more important.
Why is that?
Because it can really speed up AI development.
Ah.
Instead of spending months or even years trying to find the best model,
right,
you can let an algorithm do it for you.
So it frees up researchers to focus on other things.
Exactly, like the really hard problems that still need to be solved.
So this author, they explore auto ML and auto DL in the context of both audio and video processing.
Right, showing how it can be used in different domains.
This is really cutting-edge stuff.
It is.
Now let's jump to something that's even more cutting-edge.
Okay, I'm ready.
Vision transformers.
The VITs.
Yeah, these are like the new kids on the block.
I've heard about them. Are they going to replace CNNs?
Well, some people think so.
Interesting.
They're definitely challenging the status quo.
So what makes them so special?
Well, unlike CNNs, which use convolutional operations to extract features,
Right.
VITs use something called self-attention.
Self-attention.
Yep, and that allows them to capture these long-range dependencies within an image.
Oh, okay, so they can see the bigger picture.
Exactly, and that can be really useful for tasks like object detection
Right.
and image segmentation.
But aren't they computationally expensive?
They can be.
So?
But their ability to learn from larger data sets and capture more complex relationships often outweighs that cost.
So it's a trade-off.
It is. And there's been a lot of research lately focused on making VITs more efficient.
That makes sense.
Now, this author, they specifically address a challenge with VITs.
Which is?
Rotation invariance.
Ah, okay.
CNNs, they have a natural bias towards translation invariance.
Meaning?
They can recognize objects no matter where they are in the image.
Right, a cat is a cat, whether it's in the top left corner or the bottom right corner?
Exactly. But with VITs, it's harder to achieve rotation invariance.
So if you rotate the image...
The VT might not recognize the object anymore.
Got it.
So how do these authors solve this?
Okay, I'm all ears.
They came up with a new embedding layer method that uses self-attention
Wow.
to make the VTs robust to both local and global rotations.
So they can handle any kind of rotation.
Pretty much. And the results were really promising.
They work.
The author's method significantly improved the robustness of VVTs against rotation.
Without sacrificing performance.
Exactly. And it generalized well to other tasks like object detection.
That's impressive.
This author is really pushing the boundaries of what's possible with VVTs.
Yeah, they're doing some amazing work.
And this brings us to a key theme that runs throughout this dissertation.
Okay, what's that?
Inductive biases.
Inductive biases.
Yeah, those are basically assumptions that we bake into our models about how the world works.
Right.
Like the convolutional layers in a CNN introduce a bias towards translation invariance.
Because we assume that objects can appear anywhere in an image.
Right, a cat is still a cat no matter where it is.
Exactly.
But as we've seen with the work on rotation invariance in VTs, designing these biases can be tricky.
It is.
You want to introduce biases that help the model generalize,
right,
but you don't want to introduce biases that could lead to unfair or discriminatory outcomes.
That's the danger.
It is. And this author's work really highlights the importance of carefully considering these biases and mitigating potential problems.
Throughout the entire AI development process, from data collection to model training to evaluation and deployment.
It's a holistic approach.
It has to be.
So we've covered a lot of ground in this dissertation.
We have RBFs, feature response maps, motion artifacts, vision transformers, inductive biases.
It's a lot.
It is, but it's all connected.
It is. So for our listener out there, what's the key takeaway? What's the big picture message here?
I think the main message is that building truly robust, fair, interpretable, and explainable AI, it's a journey. It's not a destination.
We're still figuring things out.
We are, but this dissertation shows that we're making progress.
Yeah, it's really inspiring work.
It is.
It gives me hope for the future of AI.
Me too.
This author is a real trailblazer.
Absolutely.
They're pushing the boundaries of what's possible.
And making us think critically about the ethical implications of our work.
Exactly.
Which is so important.
It is.
We can't just focus on performance. We have to consider the broader impact of AI on society.
Absolutely.
So this dissertation, it's a call to action.
A call to action
for all of us working in AI.
To build systems that are not only powerful,
but also trustworthy.
Transparent.
And beneficial to humanity.
Well said.
Thanks.
This has been a fantastic deep dive.
I agree.
So much to think about.
Definitely.
I'm really glad we had this conversation.
Me too.
It's given me a lot to ponder.
Same here.
And I'm sure our listeners feeling the same way.
I hope so.
This is the kind of research that really pushes the field forward.
It is. It's groundbreaking.
And it's exciting to see where it leads.
Absolutely.
Well, I think that's a good place to wrap up part 1 of our deep dive.
Sounds good.
We'll be back soon with part 2.
Looking forward to it.
Where we'll delve even deeper into this fascinating dissertation.
Can't wait.
Until then, keep exploring, keep questioning, and keep pushing the boundaries of what's possible with AI.
Excellent advice.
See you next time.
See you then. And they're great at capturing both global context and local details.
Which is important for
getting rid of those pesky motion artifacts.
Okay, so the architecture makes sense and the training.
Well, they created this whole deep learning pipeline.
Oh, cool. Tell me about it.
It's got three main parts: a projection enhancement network, or PENet for short.
Okay.
Then there's a volume enhancement network, that's the VENet.
Got it.
And then they tie it all together with this dual domain optimization approach.
Dual domain, huh?
Yeah, if you look at figure 5.2 in the dissertation, it shows the whole pipeline visually.
So break it down for me. What does each part do?
All right, so the PENet, it works on the 2D X-ray projections.
Before the 3D reconstruction.
Yeah, it's like a pre-processing step.
Okay.
It tries to clean up those projections
Perfect.
by correcting for motion artifacts, but in the projection domain.
In the projections themselves.
Yep. Then those enhanced projections,
They go into
they get fed into a classical reconstruction algorithm.
like FDK or ICBCT.
Right, to create a 3D volume.
Okay.
And then that volume goes into the VENet.
Ah, so it's like a two-step process.
Exactly. The VENet takes that initial reconstruction and it refines it further to reduce any remaining artifacts.
So you're tackling artifacts in the projections and then again in the 3D volume.
Yep, dual domain optimization.
And that's where the real magic happens.
It is. The cool part is that they train the PENet and the VENet together.
At the same time.
Yep, using supervised learning.
So they're learning how to work together.
Exactly. They complement each other.
That's amazing.
And the results are impressive.
So it works.
It does. They saw significant improvements in image quality.
Like what kind of improvements are we talking?
Well, they got up to a 6.3 dB increase in peak signal-to-noise ratio.
That's PSNR.
Yep, and a 0.19 improvement in structural similarity index. Right. For both FDK and ICBCT reconstructions.
So that means clearer images.
Definitely more reliable, too.
Which is crucial for
accurate diagnosis and treatment planning.
in radiation therapy.
You got it.
This is really impressive stuff.
It is. This author is doing some amazing work.
And it's not just limited to motion artifacts.
No.
Chapter 6 of the dissertation covers a bunch of other applications.
Really? Like what?
Emotion recognition.
Wow.
Auto ML.
Okay.
Even fairness in facial recognition systems.
That's a hot topic.
It shows how versatile this author is.
Yeah, and how widely applicable their research is.
We probably won't have time to dive deep into all of that today.
Right.
But can you give us a quick overview of the work on homogenizing CT scans?
Sure. So this is all about dealing with variability across different CT data sets.
Which is a problem for...
It's a big problem for deep learning models.
Because
if you train the model on one data set and then try to use it on another one, it might not work very well.
Why is that?
Because the data sets might be different,
In what way?
Well, the standards might be different.
Ah.
Or the acquisition protocol.
Or the patient populations.
Exactly. So the images might look different, even though they're supposed to be showing the same thing.
So how did the author address that?
They used convolutional autoencoders.
Interesting.
To learn a shared latent representation across the different data sets.
So they're basically making the scans more similar.
Exactly. Homogenizing them so the models can generalize better.
That's pretty clever.
It is. It is. And it involves, thinking carefully about the data we use, the algorithms we choose, and how we measure success.
So it's not just about making the models more accurate.
Right. It's about making them more responsible, too.
Okay, so fairness is a big part of this dissertation.
Definitely.
Now let's shift gears a bit and talk about automated data analysis.
You mean like AutoML and AutoDL?
Exactly.
Okay, so this is basically about using AI to help us build other AIs.
Right. It's like automating the process of building machine learning and deep learning models.
Exactly. And that can be really helpful because finding the best model for a given task.
It can take a long time.
It can take forever. You have to try all these different architectures and tune all these hyperparameters.
So AutoML and AutoDL.
They can automate that process.
Making things faster and more efficient.
Exactly. And freeing up researchers to focus on the more creative aspects of AI development.
So this author,
they
explore AutoML and AutoDL in the context of both audio and video processing.
Right, showing that it can be applied to different domains.
This is really fascinating stuff.
It is. It's like the future of AI development.
Okay, now let's dive into something even more futuristic.
More futuristic than AutoML.
Yeah, I think so. Vision transformers?
VITs. Okay, I've heard of them. Are they going to replace CNNs?
Well, that's the big question, isn't it?
It is. Everyone's talking about them.
They're definitely shaking things up in the world of computer vision.
So what makes them different from CNNs?
Well, CNNs, they rely on these convolutional operations.
Right, to extract features from the image.
Exactly. But VETs, they use a mechanism called self-attention.
Self-attention. Okay, I'm not familiar with that.
So basically, it allows the model to focus on different parts of the image.
Okay.
and to understand the relationships between those parts.
So it's like they can see the bigger picture.
Exactly. And that's really useful for tasks like object detection and image segmentation.
But I've heard that VITs are computationally expensive.
They can be, yeah.
So is that a problem?
It depends on the application.
Okay.
For some tasks, the benefits of VITs outweigh the cost.
Because they can achieve higher accuracy.
Exactly. And there's a lot of research going on right now to make VITs more efficient.
That makes sense.
Now, this author,
Yeah.
they specifically address a challenge with VITs.
Which is?
Rotation and variance.
Rotation and variance.
Okay. So CNNs, they have this built-in bias towards translation and variance.
Meaning they can recognize an object regardless of its position in the image.
Exactly.
Yeah.
But with VITs,
Not so easy.
they're not naturally rotation invariant.
So if you rotate the image...
The VIT might not recognize the object anymore.
Ah, okay, I see the problem.
So how did this author solve this?
I'm curious.
They came up with this clever embedding layer method
Okay.
that leverages self-attention.
To make the VITs robust to rotations.
Exactly. Both local and global rotations.
Wow. So they can handle any kind of rotation.
Pretty much. And the results were impressive.
They worked.
They did the method significantly improve the robustness of VITs against rotation.
Without sacrificing performance.
Exactly. And it generalized well to other tasks too, like object detection.
That's amazing. This author's really doing some groundbreaking work with VITs.
They are, and this brings us to a really important theme that runs throughout this dissertation.
Okay, what's that?
Inductive biases.
Inductive biases.
Yeah, these are basically assumptions that we build into our models about how the world works.
Right.
Like with CNNs, the convolutional layers introduce a bias towards translation invariance.
Because we assume that the position of an object in an image doesn't affect what it is.
Right. A cat is still a cat no matter where it is.
Exactly.
But as we saw with the work on rotation invariance in VTs, designing these biases can be tricky.
You want to introduce biases that help the model learn and generalize.
Right.
But you don't want to introduce biases that could lead to unfair or discriminatory outcomes.
Exactly. It's a delicate balance.
It is.
And this author's work really emphasizes the importance of carefully considering these biases.
Throughout the entire AI development process.
From data collection to model training to evaluation and deployment.
Right. We have to be vigilant at every step.
Absolutely.
Yeah.
Okay, so we've explored a lot in this dissertation.
We have. It's been quite a journey.
It has RBFs, feature response maps, motion artifacts, VITs, inductive biases.
And so much more.
So for our listener out there, what's the key takeaway? What's the big picture message here?
I think the main takeaway is that the pursuit of robust, fair, interpretable, and explainable AI, it's an ongoing process.
We're not there yet.
We're not. But this dissertation shows that we're making progress.
Yeah, it's really inspiring work.
It is. It gives me hope for the future of AI.
Me too. This author's a real trailblazer.
Absolutely. They're pushing the boundaries and asking the tough questions.
And making us think critically about the ethical implications of our work.
Exactly, which is so important.
It is. We can't just focus on building powerful AI systems.
Right. We have to make sure those systems are aligned with our values.
And that they benefit society as a whole.
Absolutely.
Well said. This has been an incredible deep dive.
I agree.
So much food for thought.
Definitely. I'm still processing everything we've discussed.
Me too. And I'm sure our listeners feeling the same way.
I hope so.
This is the kind of research that really pushes the field forward.
It is. It's exciting to see where it leads.
Absolutely. Well, on that note, I think it's time to wrap up this deep dive.
Sounds good.
Thank you so much for joining me on this journey into the world of robust, fair, interpretable, and explainable AI.
It's been a pleasure.
It has. Until next time, keep exploring, keep questioning, and keep pushing the boundaries of what's possible with AI.
I will. You too.
Take care.
You too.